We've recently learned about this idea called the derivative, and we've taken derivatives. We are slowly learning how to differentiate. This is one of the core skills of a differential calculus student, knowing how to take derivatives of functions. There are a lot of rules that we developed. We've proven through the definition of the derivative. Here are some of them. This is our results of calculus PDF that we have on the Canvas page. We know that if a function is differentiable, then it's continuous. We know we have this fancy thing called the power rule for the natural numbers. So it started with just the natural numbers. For instance, let me grab a good color here. I like this color. If I know that y is equal to x to the power of 7, then that means that y prime is equal to 7 times x to the power of 6. That's a famous power rule we have to super get used to. If y is equal to x, that means that y prime is equal to 1. Things like this. Those are all given by the power rule for the natural numbers. Remember, the natural numbers are the set of whole numbers, 1, 2, 3, and so on. And then we have these famous derivative rules. Many of these were proven in class. If you have a constant function, that means the derivative of a constant function, a horizontal line, is clearly going to be 0. Remember, the derivative really is just a code name for slope. We have this law right here. If you have a number times a function, then the number kind of just hangs out as you take the derivative of the function. For instance, if I have maybe z is equal to 7 times the sine of theta, that means that z prime is equal to 7 times the cosine of theta. So I really just took the derivative of this part, and the 7 just hung out as I took the derivative of this function part. That's what this one's saying. Then, of course, we have the derivative of a sum is the sum of derivatives, the sum rule for derivatives. And these two guys are famous because they're counterintuitive. This is where, unfortunately, you can't simply say that the derivative of a product is the product of derivatives. That's false. We have to follow this thing called the product rule. And we've seen a few examples of that getting used. Super important. For instance, I'll do a quick example for all of these. So if I have that y is equal to maybe the square root of t times, I don't know, the tangent of t. That's kind of horrible, but that's okay. That means that y prime is equal to the derivative of this first function, which we have proven in class to be 1 over 2 root t, times the second function, untouched, tangent of t, plus the derivative of the second function times the first function untouched. So we got secant squared of t. All right. Famous derivative of tangent is secant squared of t. That is an immediate application of the product rule right here. We also have this thing called the quotient rule, which we also cannot get enough of. In fact, you can prove the derivative of tangent using the quotient rule. You can prove all sorts of things using the quotient rule, including, let's see, do I want to show a quick example of the quotient rule? Yeah, sure, why not? So let me grab a quotient. What if I have that, I don't know, r is equal to, I'll do t divided by the cosine of t. Then r prime by the quotient rule is going to be this bottom function. Don't touch it. Don't change anything. Cosine of t times the derivative of the top function. But the derivative of t with respect to t is just 1. Minus the top function times the derivative of the bottom function. The derivative of cosine is minus sine of t. All divided by the denominator squared, which is going to be cosine squared of t. And let's see what that leaves us with. It looks like we got something like the cosine of t. So this is an immediate application of the quotient rule. Plus t times sine of t. All divided by cosine squared of t. And of course, there's different trigonometric ways you can express this. For instance, that's the same thing as secant of t plus t times secant of t times tangent of t And you might ask, huh, that's interesting, because it looks like I have the secant of t right here, and here's the derivative of secant of t. So I wonder if there was a different way I could have differentiated. Indeed, you could have forced this to be a product rule, not a quotient rule. So think about why that's true. Okay, so that's an application of the quotient rule. And then let's see what we got next. Okay, so we developed the power rule for the integers. Recall that the integers are the set of the whole numbers, the naturals, and their negatives, and 0. For instance, we now know how to take derivatives of things like, if I had y is equal to x to the -3, we know that because of this power rule for z, that I can just do the typical power rule, same story, y prime is equal to -3 times x to the -3 minus 1, but that's -4. So we expanded the power rule to the set of integers, and then here's where really kind of differentiation gets going. This is where all of a sudden all sorts of rules can kind of fall out, and that's the chain rule. We gave a little bit of a sort of a proof sketch of the chain rule in class, and to keep this video short, I'm not going to do it again, but we will see some applications of the chain rule in this video. Wildly, wildly powerful differentiation tool. To immediately see why this is useful, we can actually prove that the derivative of cosine is negative sine using the chain rule. And I think I'll do that real quick. So let's try to find the derivative of the cosine of x using the chain rule. And what I'm going to assume is that we already have the derivative of the sine of x. Recall that to find the derivative of cosine, you could simply use the limit definition and prove it that way and some trig identities. But now that we have the chain rule, there's actually a much cleverer way to do this. And here's how I'm going to do it. This is going to be the same thing as the derivative of the sine of pi halves minus x. Okay, so this is called the complementary angle identity for the cosine function. This is something we remember in trigonometry. And you should really just think about a right triangle and why this is actually quite obviously true. But now that we have the chain rule, what we could actually do is prove that the derivative of cosine should be negative sine. So let's see how that goes. To use the chain rule, notice that I have the composition of functions. The outside function is sine here, and the inside function is this pi halves minus x. So in applying the chain rule, what I'm going to do is take the derivative of the outside function, that is sine of theta, or sine of something, which is, the outside function is sine, and its derivative is the cosine. And then I evaluate this at the inside function. But the chain rule dictates that I then need to multiply. So again, the inside function is pi halves minus x. I then have to multiply by the derivative of the inside function. But wait a second. The derivative of pi halves is just 0. So this is going to go to 0. The derivative of minus x is just going to be the number hanging out outside of or next to x, which is -1. So I think this is going to be the same thing as the cosine of pi halves minus x times -1. Oh, but that's the same thing as negative cosine of pi halves minus x. And that is the same thing as, so that we're going to do the opposite complementary angle identity on sine and cosine. Indeed, this thing is the same thing as sine. That's not a calculus fact, that's a trigonometry fact. So the cosine of pi halves minus x is the same thing as the sine of x. That's what I'm going to use right here. I'll use a little bit of a justification. So this is because the cosine of pi halves minus anything is the sine of that thing. And I use the opposite one up here. So this one was because the cosine of anything is equal to the sine of pi halves minus that thing. All right. So again, and this is of course the chain rule right here. Really powerful tool, this chain rule. We just used it to skip a huge nasty limit definition. And what the big thing we're going to do next is we are going to expand this power rule even further. So we have the power rule for the naturals. We have the power rule for the integers. And we're going to use this chain rule and the power rule for the naturals and the power rule for the integers to prove the power rule for the quotients. A little bit of review. Q is like the set of fractions. Indeed, once we have expanded our power rule for the quotients as well, if we have functions, maybe something like this, y equals x to the 4/3. Notice that 4/3 is not an integer. 4/3 is not a natural number, so we technically don't have any tools to do this yet other than the limit definition, which would be chaos. But using this chain rule, we can prove that the power rule for the rationals works as well, leaving us with this guy's derivative. Y prime is the same thing as 4/3 times x to the 4/3 minus 1, which is x to the 1/3. So indeed, the power rule also works for the rationals. Let's see a proof. The power rule for Q. So what I'm going to begin by is I'm going to let Q be a rational number. And I'm also going to let f of x equal x to the power of Q. I'm going to hope, or what our goal is to prove that f prime of x is the same thing as Q times x to the power of Q minus 1. All right, that's what we expect. All right, let's see the proof. Again, like I said, like I hinted at, we should use the power rule for the integers, we should use the power rule for the naturals, and we should use the chain rule. What I'm going to begin with is let Q be a rational number. And what this means, by definition of the rationals, is that Q is equal to A divided by B, where, again, Q is a fraction, where my numerator is an integer and my denominator is a natural number. Okay, that's really crucial. And what I'm also going to do is let f of x equal x to the power of Q. Then what I could do is replace Q with this new definition. So f of x is equal to x to the power of a over b. All right, so this would be because Q equals a over b. I'll do a nice style proof here. But what does this mean? Oh, that means that if I raise both sides to the power of b, what I would have is f of x raised to the power of b is equal to x to the power of a. All right, so I guess I could say this is because, in general, if I have something like, well, let's see, a to the power of, let me do it like this, or a is equal to b to the power of c over d. That implies that a to the power of d, it's kind of like I'm raising both sides to the power of d. And I am kind of assuming things are well behaved. Then these two guys come together via multiplication. D's cancel, leaving me with a to the power of d is equal to b to the power of c. And we are assuming like nice properties on what a is and b is. This is an idea for the power rule for the rationals. So recall that b is a natural number. B is a natural number. A is an integer. So what I could do is take the derivative on both sides of this equation. That's huge. Notice that up until the chain rule, I didn't know how to take a derivative of this. But this is the composition of two functions. somebody plugged f of x into this other function, which is something raised to the power of b. I know how to take the derivative of something to the power of b because b is a natural. I have the power rule for the natural numbers. I also have the power rule for the integers. So let's take derivatives on both sides. And on the left-hand side here, I take the derivative of the outside function. That's going to be b times f of x raised to the b minus 1, right? Oh, but that's the same thing, or excuse me, I then have to apply the chain rule and multiply by the derivative f prime of x. Notice, that is what I'm actually solving for. I'm trying to show that this thing right here is q times x to the power of q minus 1. So I want to isolate this. On the other side of my equal sign, I have the power rule for the integers. So this is really, honestly, in this one step, this is where I'm using all of my big machinery. And the rest is going to be really calculus. So I have x times, or a to the times x to the power of a minus 1. Okay, so this is power rule. I was able to do that because of the power rule for n, z, and because of the chain rule. Absolutely huge. All right, so now what the heck do I do? This implies that f prime of x, the rest is really just algebra, you guys, is equal to a times x to the power of a minus 1 divided by b times f of x to the power of b minus 1. Oh, but wait a second. What the heck was f of x? Okay, this is huge. This is the same thing as a over b times x to the power of a minus 1, all divided by f of x to the power of b minus 1. But what was f of x? Oh, look right here. F of x is the same thing as x to the power of a over b. So that's what I'm going to replace this with. Then we have to remember our exponent rules, all of our algebra. All of it was really, I really think algebra is all simply a tool for you to later do calculus. Algebra is and this is what Euler said. This is why I made that history video. Euler said, look, all of this algebra, all of these algebraic manipulations are so crucial for studying this calculus of change, or this science of change, which is calculus. And that's why Euler and Agnesi made these amazing mathematics textbooks. Know your algebra, know your trigonometry. That will smooth over calculus so much, and you'll really see its beauty. All right, so exponent rules. All of that to say, exponent rules. What we have is my numerator is going to stay the same. I'm going to do one step at a time. But my denominator, when you have something raised to a number, and then that whole thing is raised to a new number, these two things come together via multiplication. In other words, what I have is a over b times b minus 1. All right. Oh, but what is that? That's the same thing as a over b times x to the a minus 1 divided by x to the power of a over b times b minus a over b. That's just the distributive property. It's an axiom. Oh, but that's the same thing as a over b times x to the power of a minus 1, all divided by x to the power of a, notice these guys cancel, the b's cancel, minus a over b. But also, remember your exponent rules. Here, I'll quote my exponent rules. This is like if I have a, well, maybe I don't want to use a, theta to the power of m all to the power of n is the same thing as theta to the power of m times n. This is just the distributive property. And what I'm going to say next, I guess this is the identity, or excuse me, the inverse property. What I'm going to say next is this. This is the same thing as a over b times x to the power of a minus 1 minus, in parentheses, a minus a over b. Okay, crucial. Why is that true? So theta to the power of m divided by theta to the power of n, that is the same thing as theta to the power of m minus n. Remember your exponent rules and just these definitions of exponents. And this is the final sprint, you guys. A over b times x to the power of a minus 1 minus a plus a over b. A's cancel. Check this out. I have a over b times x to the power of a over b minus 1. Oh, wait. A over b is the same thing as q. And what we just did is we said that the derivative must necessarily be equal to q times x to the q minus 1, which means that the power rule holds for the rational numbers as well. Absolutely huge, guys. So what we just did, here's where we're at. Check, we've proven it. Check, I don't like that color. Check, we've proven it. Check, check. All the way up to here, we've proven all these rules. We are going to keep going because my big goal for today, first of all, I want to talk about a new function, e to the x. Absolutely crucial function right here. I want to show, really almost by definition, this is the special function whose derivative, so here's the function e to the x, here's its derivative, and notice that it is the original function. That's wildly powerful. I want to talk about this a little bit. It won't take too long. We did introduce this function in class, but I want to talk about this function's inverse, which we are all familiar with from algebra, and that is the log of x. It looks like on this document I wrote logx. That's what I call this, but most people call this the natural log of x, and that's what it is. Mathematicians just call it log x instead of the natural log of x, but that's what this is. I want to talk about its derivative because that is something we definitely need to know. The derivative of the natural log of x is famously equal to 1 over x. And we're going to prove that today. We're also going to reintroduce this e to the x. And I think my final goal in terms of proofs for today are to get to here. Let's also look at how powerful this is. We just proved the power rule for the rationals. I want to also prove it for, last but not least, the real numbers. And once I have this guy and this guy, which is what today is dedicated to, I think we'll be able to prove that it also holds for the real numbers. And let's see how all this goes. Okay. Let's reintroduce ourselves to e to the x. Say f of x is equal to a to the x, where a is an element of this set. It's a positive number that isn't 1. That's what that says. I want to talk about what f prime of x is. Well, by definition, of course, the f prime of x is the limit as h approaches 0 of a to the x plus h minus a to the x, all divided by h. Oh, but shoot, that's the same thing as the limit as h approaches 0. Again, remember your exponent rules of a to the x times a to the h minus a to the x, all divided by h. Okay, that's the same thing as the limit as h approaches 0 of a to the x times a to the h minus 1, all divided by h, okay? But check this out. A to the x is going to stay a to the x. I don't really care what h does. So what I can do is, relative to h moving, a to the x is a constant. So I can take it outside of the limit. This is a to the x times the limit as h approaches 0 of a to the h minus 1 over h. And then check this out. I'm going to do a little bit of sleight of hand. This is the same thing, of course, as a to the x. But then I'm going to rewrite this just a little bit. The limit as h approaches 0. And you're probably going to think, well, why did you just write it like that? But at least hopefully agree with me that this is true. So overall, what I just said was that a to the h is the same as a to the 0 plus h. Or really what I said was h is the same thing as 0 plus h. I also said that 1 is the same thing as a to the 0. But why am I saying this? Because I want us to recognize that this thing is simply the derivative of my original function at 0. Okay. So, to emphasize, what I have is that the derivative of this function right here, a to the x, is equal to, well, a to the x again. So a to the x again times the derivative at 0. So let me write that down. And then we ask ourselves, and this is where E comes into play, the definition of E. It would be so nice, maybe write it like this. A to the x is the same thing as f of x. So f of x times f prime of 0. We ask ourselves, it'd be so nice if we had a function whose derivative was simply equal to the original function. In other words, the rate of change of the function at any x value is the same as the output of the function. That would be really nice. But in order for that to happen, we must have that this thing is equal to 1. So let's just grab the number that does that. In other words, by definition of E is the number such that this thing, this limit, when I replace a with E is the fancy number a such that this limit is equal to 1. So the E, we're choosing the number that forces this to occur. So to write that down, in other words, if f of x is equal to e to the x, then f prime of x is equal to, e to the x times f prime of 0, but we just chose e so that f prime of 0 is equal to 1, e to the x. All right, huge. E to the x is a very special function. It is its own derivative. And that shows up all of the time. So to kind of just immediately see this in an application, let's suppose I had y is equal to e to the power of, 3 times sine of x. This is a chain rule problem. To take the derivative, y prime, I have to take the derivative of the outside function, which is e to the something. But the derivative of e to the something, as we just said, is going to be e to that thing. So this would be e to the 3 times sine of x times the derivative with respect to x of 3 times sine of x. And of course, this is the same thing as e to the 3 times sine of x times 3 times cosine of x. Derivative of sine is cosine. And I would clean this up like this. This is the same thing as 3 times e to the 3 sine of x cosine of x. And there's a beautiful relationship, by the way, between these trigonometric functions and this exponential function. That's what this is called, by the way, exponential function. Beautiful relationship that Leonhard Euler really picked up on, who we just learned about. That guy would not shut up about amazing mathematics. This is called the exponential function. Super, super powerful function. It is the function, the non-zero function, who is its own derivative, whose slope at every x value is the same as the output at every x value. And here's a quick little application of how to take derivatives. We'll get a lot more practice in this week's practice video. But I actually want to immediately talk about, and by the way, we should have seen e to the x before in algebra. Like when I'm teaching algebra right now, and I just introduced this guy. And I'm also about to talk about inverse functions, which is something we remember from algebra as well. Something to remember. E to the b, say, is equal to, I'll do other symbols. Like if I had e to the star is equal to square, that is true if and only if the natural log, so this is the inverse, of square is equal to star. All right, so this sort of like flip-flop action. Notice in this case that the star is the input and square is the output, where in this case over here, square is the input and star is the output. Really, this natural log is what undoes the exponential. It's almost like, I kind of imagine it like e can hop over the equal sign, but when it hops over the equal sign, it becomes its inverse function, and that's really kind of bad mathematics, but it just helps you kind of imagine what's going on here. And using this idea, we're actually going to figure out what the derivative of the natural log is. So let's find out. In other words, to go back to our derivative rules, what we just did is we talked about this. That's great. We now want to talk about this guy's derivative. So I'm going to say, let's let f of x equal the natural log of x. And let's try to compute the derivative. We, again, will need the chain rule. So let f of x equal the natural log of x. Okay, so how am I going to find the derivative of f of x? Well, I'm going to use this rule. I have something that kind of looks like this here. If you look, it looks like the thing that's on the inside of the natural log is a square. The thing on the inside of the natural log in this case is the x, so I'm going to kind of do this just to help us see it. It kind of looks like the square. And then what that equals, so what the natural log of square equals, is the star. So this kind of looks like the star. That was supposed to be a star. And what I want to do is take it from this translation, that's what we're seeing right here, over to this world. So what I would have is e to the power of star, but star is f of x. So what that is e to the power of f of x is equal to square. But what is square? Square is simply the thing on the inside of the natural log, which is x, all right? And I really want to figure out what f prime is, so what I'm going to do is take the derivative on both sides. So this is by definition of natural log, or I mean, this is really because of this rule up here. But I'll write definition of natural log and e to the x, natural log of x and e to the x, or really the definition of inverse functions. And now what I'm going to do is the chain rule. So I want to take the derivative of the outside function on this side. The outside function is e to the something. But remember, the derivative of e to the something is e to the something. So I'm going to write e to the f of x. But then I have to follow the chain rule. In other words, I have to multiply by the derivative of that inside function. And the derivative on the other side is 1. So the derivative of x is 1. So this was really because of the chain rule. And I want to get f prime of x by itself. So how I'm going to do that is divide both sides. F prime of x is equal to 1 divided by e to the f of x. That's just because of division. And then I simply ask myself, wait a second, wasn't there another name for e to the f of x? Sure was, and we're already there. So that's a quick justification for why the derivative of the natural log of x is 1 over x. That's something we need to know. Quick application. What if I had something like this? Y is equal to 3 times the natural log of, I don't know, x to the 4th. All right. So with this new rule, what I would have to do is y prime, if I wanted to take the derivative, the 3 just hangs out. It's simply a number. y prime is equal to 3 times the derivative of the natural log of x to the fourth power. But what I'm going to do is first take the derivative of the natural log, which is going to be 1 over whatever the thing on the inside of the natural log is, which in this case is x to the fourth. But then what I have to do is multiply that by the derivative of the inside function. Okay, and that's x to the fourth, and that's easy enough. What I have is 3 times 1 over x to the fourth times 4 times x cubed. All right. And notice there's a lot of cancellations that happen. So what I have is 12 times 1 over x. In other words, 12 over x. And of course, those of you that are a little experienced with the natural log, you're probably screaming at me from the very beginning. How about you use your log rules first? And I completely agree. That is the way to do this question. So method 2. Y is the same thing as 3 times 4 times the natural log of x. All right, so famous log rule. This guy, if it's in the input raised to a power, this number can come outside in front of the natural log. Be careful, that is not the power rule. That is simply a pure property of the natural log that we learned in algebra. In fact, this step from here to here involved no calculus. No calculus involved, purely algebra and definition or properties of this natural log. But that does make this derivative much easier, because what I have is simply 12 times the derivative of natural log. And we just proved that the derivative of the natural log is 1 over x, giving me a final answer of 12 over x. All right, super powerful. We now have new tools. So to emphasize where we're at in this results of calculus, this has been justified, and now this has been justified. So the derivative of the natural log of x, 1 over x, we got to know that. The derivative of e to the x is e to the x again. We have to know that. These other guys will be indirectly sort of discussed in this week's practice video. I got to get going here. So last thing I want to do in terms of like proving stuff is let's prove this power rule once and for all for the real numbers. This is powerful. Notice that we kind of walked up this set chain. We had the power rule for the naturals, and then we proved the power rule for the integers using the quotient rule, and we proved the power rule in this video for the rationals using the chain rule. And what we're about to do is prove the power rule using this logarithm and exponential function for the real numbers. So let's see. The power rule let's let alpha be a real number, and let's let f of x equal x to the power of alpha. Then f prime of x is equal to alpha times x to the power of alpha minus 1. In other words, once we have this, I can do crazy things like this. If y is equal to x to the power of pi, then I would know that y, up until this point, I would not know how to take the derivative here. But now I will know that y prime is the same thing as pi times x to the pi minus 1. Power rule works for even these transcendental numbers. If y is equal to x to the power of the square root of 3, then y prime, the derivative of y, is root 3 times x to the power of the square root of 3 minus 1. Power rule works for all real numbers. Let's see the proof. Slick. This is a clever proof now that we have the exponential function. Let f of x equal x to the power of alpha, where alpha is a real number. So this is just the setup. Alpha is a real number. Let's see. I have to think here. Well, what I'm going to do is this. I'm going to take the natural log of both sides. Honestly, I'm kind of winging it. I haven't done this proof in a while. But this seems promising. Something I'm noticing is I can all of a sudden use a log rule. So again, no calculus. This implies that the natural log of f of x is equal to alpha times the natural log of x. No calculus. So this is because of, so if I have the log base a of b to the c, this is equal to, proven in algebra result, not a calculus result, log base a of b. C times log base a of b. This c can come out front of the logarithm. So that's all I've done. But now what I think I want to do is take the derivative on both sides here. Check this out. Yeah, this is going to work. The derivative of the natural log of something is 1 over that thing. But I have to follow the chain rule. I have to multiply by the derivative of the inside function. Okay? Now, on the other side, I simply have a number times the derivative of the natural log of x. But we just showed that that's going to be 1 over x. All right? In finding, and this object right here is what we are looking for. So what I'm going to say is this implies that f prime of x is equal to alpha times 1 over x times f of x. Oh, but wait a second. That's the same thing as alpha times 1 over x. What was f of x again? Oh, yeah, it was x to the power of alpha. And just immediately, that tells us that the derivative of f is alpha times, using exponent rules here, x to the power of alpha minus 1. So again, that's because if I have, I think we already used it, theta to the power of m divided by theta to the power of n, that is the same thing as theta to the power of m minus n. That's what was used from here to here. Powerful. We did it. I keep saying powerful, and it's the power rule. So, all right, we can now use the power rule for any, for x raised to the power of any number, any real number. We haven't proven it for the complex numbers, but actually this proof would actually also work for the complex numbers. All right, guys, so we just did a lot. Here's where we are at. All of this stuff that's underlined in light blue are things we have accomplished and shown to be true. We have proven these guys. And in blue, next week's video, which I'll release soon, and also all of these we do know. I do assume we know all of these. We proved this earlier in the video, this one right here. And I think this is proven with the quotient rule. This can be proven with the quotient rule, and so can these. So all of these are tools in our backpack, all been shown to be true. And honestly, the tactics that we've seen today can be used to show that these guys are true. They're not too hard. You have to remember your logarithm rules, your non-calculus prerequisite logarithm rules, very important to show these dark blue sort of results. But in the future, we do need to know these results. But I don't memorize stuff. I just kind of re-derive this using mathematics. That's what a mathematician should do. All right, but I had a couple examples that I wanted to go over before finishing this video because they're very similar to examples that you could get. Look at how much we've done. Awesome calculus here. Very similar to examples that you might get on your exam coming up in about a week. So let's read this. Suppose that functions f and g and their derivatives with respect to x have the following values at x equals 2 and x equals 3. All right, so I have a chart of values for the functions and their derivatives. What this says is f of 2 is equal to 8. What this says is the slope of f at 2 is equal to 1/3. This says that the slope of g at 2 is equal to -3, and so on. It's a crazy slope right here. So the slope of f at 3 is 2 pi. I wonder if that's going to be used. I don't know. We want to find the derivatives with respect to x of the following combinations at the given value of x. All right, so let's check this out. We have all of these we got to take the derivative of. I don't know if we can do it here. I wonder if I just zoom in. I mean, yeah, I feel like that's going to work. Let's see if I can crowd this up. All right. So the derivative of 2 f of x, and this is going to be a good review of all of our differentiation rules. To make this go as smoothly as possible, I would have this chart with you right next to you. I can't keep doing all this crazy zoom in and zoom out. It makes, it's hard to watch. So I'll try to minimize that, but I will reference these rules as I take these derivatives. And these are all things that we've developed together as a class. All right, zooming back in. What we have is the derivative with respect to x of 2f of x is equal to 2 times the derivative with respect to x of f of x. But that is the same thing as 2 times f prime of x. Those are synonyms. But we want this at 2. So what I can do is replace x with 2. So I can say maybe like this, at x equals 2. This will take us to 2 times f prime of 2. But what is that equal to? I don't know. That's going to be 2. And I just have to read the chart. F prime of 2. F prime of 2. So I have f prime. I have 2. It's going to be 1/3. Final answer, 2/3. Easy peasy. Next. All right, so this one's also very easy. We want the derivative with respect to x of f of x plus g of x. But we know that this derivative of a sum is the sum of derivatives. So this is simply going to be f prime of x plus g prime of x. But I want to evaluate this at 3. So we want at x equals 3. That's going to be f prime of 3 plus g prime of 3. But these are both given to us in the chart. So this is going to equal, I don't know, f prime of 3 right here, 2 pi, plus g prime of 3. So we got 3 right here. F prime when 3 is plugged in is equal to 2 pi. G prime when 3 is plugged in is equal to 5. So we got 2 pi plus 5. Okay, I hope these get a little bit more interesting. All right, finally. So what we want is the derivative of the product of f and g. So in order to do that, the derivative of the product is unfortunately not the product of derivatives. We have to follow the product rule, which we have proven. This is equal to the derivative with respect to x of f of x times g of x. So what that is I grab the first function, take its derivative, and then multiply by the second. Don't change the second. And then, of course, I add to this f of x times the derivative with respect to x of g of x. Again, this is what I call the product rule for derivatives. I want to evaluate this at x equals 3. In other words, what I really need is f prime of 3 times g of 3 plus f of 3 times g prime of 3. But all of these things are given in the chart. So this is equal to, so f prime of 3 is equal to 2 pi. Maybe let me collect them. F prime of 3 equals 2 pi. G prime of 3 is equal to 5. F of 3 is equal to 3. And g of 3, based on the chart, is equal to -4. So now it's literally just plugging them into this formula right here. That's easy. So it looks like I got, this is the same thing. 2 pi g of 3, -4, plus f of 3, that's 3, times g prime of 3, that's 5. And this is the same thing as 15 minus 8 pi. Let's go. All right. And okay, so now we're getting forced to use the quotient rule. Same story. We want to find the derivative of f of x. The derivative of f of x divided by g of x. All right, so that's the quotient rule. Let's do it. Remember, the derivative of a quotient, unfortunately, is not the quotient of derivatives. But what I do is I have this little limerick. I say if I want to take the derivative of the quotient, what I do is I grab the low function, multiply by the derivative of the top function, and I hear that and go low d high. So here's low, d high, minus high, f of x, d low. It's literally how I remember it. Low d high minus high d low. Sounds like you're yodeling or something like this. All divided by the bottom function squared. But I want to evaluate this at x equals 2. So what I need is g of 2, f prime of 2, f of 2, g prime of 2, and we already have g of 2. Okay, so let's see what those values are. G of 2. 2, 8, 1/3, negative 3. Okay. Did I get that right? Yeah. Okay, now it's literally just plugging stuff in. So this is g of 2 right here. That's going to be 2. What this guy is f prime of 2. What that is 1/3. 2 times 1/3 minus f of 2. That's going to be 8. And then what we have right here is the derivative of g at 2. That's this right here, negative 3. All divided by g of 2 squared. So that's going to be 2 squared. Of course, that's 4. But let's see if this cleans up at all. This is going to be the same thing as 2/3 plus 8, what the heck, plus 24 divided by 4. I'd multiply top and bottom by 3, multiply by 1. So that's going to be 2 plus 72 divided by 12. And what we have is 1 plus 36 over 6. That's the same thing as 37/6. Final answer. All right, are these going to get more interesting? Yeah, finally, we got composition of a function. So how is this going to go? The derivative with respect to x of f of g of x is going to be the same thing as f prime of g of x times g prime of x. In other words, we want x equals 2. I don't know why I said in other words, but what we need is f prime of g of 2 times g prime of 2. And I think we have these things already set up for us. Yeah, we have g of 2. So what we need is f prime of g of 2 is 2. Oh. So again, what I just used was that g of 2 is 2. So I replaced this thing with 2. G prime of 2 is negative 3. Oh, but wait a second. We now just need to know what f prime of 2 is, and that's 1/3. Oh, they made this one look so nice. I found this from like an online source. So what I have, again, f prime of 2 here is 1/3. So I can replace this with 1/3. G prime of 2 is negative 3. Negative 1. All right, how much more do I got? 3 more. Okay. So chain rule yet again. I want to take the derivative with respect to x of the square root of f of x. Let's see how this goes. What I need to do is follow the chain rule. In other words, the outside function in this case is the square root of something. So my first step is going to be 1 over, taking the derivative of the square root of something is going to give you 1 over 2 times the square root of that thing. But then you have to multiply by the derivative of the inside function. Okay, nice. But I want this at x equals 2. So every time I see an x, I'm going to replace it with a 2. So what I want is 1 over 2 root f of 2. Horrible. 2 root f of 2 times f prime of 2. Do I know what, does that chart give me both of those pieces? This is the same thing as 1 over 2 root 8. Again, it's sneaking in right here on the screen. F of 2 is equal to 8 times the derivative of f at 2, which is 1/3. All right, so what is this? It's going to be 1 over, don't tell me. Root 8 is 2 root 2. So I got 4 times 3, 12 root 2. There you go. All right, looks like we got another chain rule here, or you can alternatively use the quotient rule. But I figured maybe let's use the chain rule here, because that's what kind of where this video is about, applications of the chain rule. I want to take the derivative of 1 over g squared of x. But that's the same thing as the derivative of g to the power, g of x, to the power of -2. Those are the same object. Again, exponent rules is what I used. But you guys, we have the chain rule and the power rule for the integers. So this is going to be the same thing as -2, power rule, what I'm using right now, times g of x to the power of 1 less than -2, -3. Then I have to multiply this by the derivative of g of x by the chain rule. That's what I just used. But I want this at 3, so at 3, what I have is -2 times g of 3 to the -3rd power times g prime of 3. So I need g of 3 and g prime of 3. G of 3 apparently is -4. G prime of 3 is 5. -4. -2 times -4 to the -3rd power times 5? And I can't remember for crud. Yeah. Okay, what's the best way to do this? This is the same thing as -10 divided by -4 to the 3rd power. This is the same thing as -10. A negative to a power of an odd number is going to be negative again, so negatives cancel. So I got 10 divided by 4 to the 3rd power. That's the same thing as, what is 4 cubed? 64. So we got 5 over 32. And that's my final answer. All right, what else? I think this is the last one. What an insane type of question, but a good question in terms of applications of the chain rule in a little bit more of an abstract sense. All right, let's do this last one. We want the derivative with respect to x of the square root of f of x squared plus g of x squared. This is the same thing as 1 over 2 root f of x squared plus g of x squared. And the reason that's my first step is because the outside function is actually going to be the square root here. So what I know is the derivative of the square root. So here, let me write it like this just so I don't get confusion. The derivative of the square root of something is equal to 1 over 2 times the square root of that something. All right, so that's the derivative of the outside function, but then of course I have to multiply by the derivative of the inside function, which is going to be that f of x squared plus g of x all squared. And what you could do is use the product rule twice, but I'm not going to do that. I'm going to use the chain rule. So let's do this. I'll do show more work. So I got f of x. I'm just rewriting right now. G of x squared. To take the derivative over here, I see a function inside of another function. That other function is something squared. So to use kind of this notation, the derivative of something squared is equal to 2 times that something. All right. In this case, what I have is 2 times f of x. But then what I need to do is follow the chain rule. I have f of x inside of another function, which means I need to immediately multiply by the derivative of the inside function, which is f prime of x. Same story on this other guy. This is going to be 2 times g of x times g prime of x. Again, that's the chain rule and the power rule for the natural numbers. I want to evaluate this at 2. So also I'm noticing that 2's are going to cancel, so that's nice. It looks like my final answer is going to be, well, this isn't my final answer, but I have f of 2 times f prime of 2 plus g of 2 times g prime of 2, all divided by the square root of f of 2 squared plus g of 2 squared. And I think f of 2, I need what f of 2 is, I need what f prime of 2 is, I need what g of 2 is, and I need what g prime of 2 is. Those are all the pieces, these little pieces that I need to figure out what this object is. And let's find out. F of 2 apparently is 8. We got f prime of 2, that's 1/3. We got g of 2, 2. G prime of 2, -3. All right. Plugging stuff in. This is the same thing as 8 times f prime of 2, 1/3, plus g of 2, which is 2, times g prime of 2, which is -3, all divided by the square root of f of 2 squared. F of 2 is 8 squared, and then plus g of 2 squared, which is 2 squared. All right, let's see what we got. This is the same thing as 8 minus 18, all divided by 3 times the square root of, what is that? Square root of, well, I'm going to do this. 4 times 8 is the same thing as 4 times 2, so it looks like I got a 2 squared. No, 4 squared. Oops. Plus 1. Am I right there? Yeah. So this is the same thing as -10 over 3, or excuse me, over 6 times the square root of 17. And of course you can simplify that further. -5 over 3 root 17. Kind of gross, but at least we are able to figure it out. This type of chart chain rule question is famous, and there's another final question of the day, famous type of question. Well, I drew this one so big for some reason. And that's if you are given like the graphs of some functions, and we need to find particular derivatives here. All right, final sprint, you guys. Let's figure some stuff out. It looks like we have the graph of f and the graph of g here. It's the graph of f. We got the graph of g. And we also have these new functions, h of x and r of x here. And we need to take these 4 derivatives. Okay, 4 derivatives shouldn't be too bad. Let's find out. Here's how I'm going to attack this. We have the derivative of a quotient here. This is the same thing as the bottom function evaluated at 1, so low, d high, h prime of 1, minus high, which is h of 1, d low, which is f prime of 1, all divided by the bottom function squared. Okay, so that was simply the chain rule, and I immediately evaluated it at 1. Then what I'm going to simply ask myself to solve this is we need 4 objects. We need f of 1, f prime of 1, h of 1, and h prime of 1. So f of 1 and f prime of 1 are going to come from the graph. So we have f evaluated at 1. So we have to think a little bit here. F is a line from 0 to 2. In order to figure out what the output of this function is at 1, so that'd be like this height right here, because this is f of 0, f of 1, f of 2, we need to figure out the slope. So let me maybe do it like this. To figure out the slope here, we have m is equal to the rise, which is, I go from 9 to 1, which means my rise is -8. So again, how do the y values change it for the rise? I go from 9 to 1. How do I do that? I subtract 8. And then how do the x values change for the run? I go from 0 to 2, which means I add 2. And that gives me -4 for my slope. And what that means is that every step I take along the x-axis, all right, every step I take along the x-axis, my output decreases by 4. So in other words, f of 0 was 9, but when I take a step, the output will decrease by 4, telling me that f of 1 is equal to 5. All right, because again, that's 9 minus 4. Figured out what f of 1 is. And luckily, we indirectly found the derivative of f at 1. The derivative of f at 1 is simply going to be the slope of this line. Remember, derivative, slope, slope, derivative, derivative, slope, slope, derivative. Those are the same, in essence, the same concept or the same object. So if we want the derivative of f at 1, so here's 1 right here. Maybe I'll label it. It's not labeled, but it's implied that this is 1. We need the slope of our function at that point, but we already have the slope. The slope of the function at that point, in other words, the derivative of f at 1 is equal to -4. All right, now I need h of 1. Notice h is defined as this gross function right here. So to find h of 1, that's going to be the square root of 1 times g of 1. To find what h of 1 is, I need what g of 1 is, which means we're probably going to have to talk about, I do know what the square root of 1 is. So h of 1 is actually the same thing as g of 1, because the square root of 1 is 1. I have to talk about this other function g here. I'm going to do something similar. The slope here, I need to figure out the slope to figure out the height of g at 1. So what is the slope here? Well, I ask myself, to figure out the rise, I go from 2 to 8. So what rise is that? That's the same thing as 6. And then the run is what I have to do to go from 0 to 6. And then I think to myself, oh, that's easy enough. That's 6. Which means that every step along the x-axis, my function g increases by 1. Because 6 over 6 is 1. I didn't write that. But if I start at 2, I take one step, that output increases by 1, which means that g of 1 is 3. All right, but now I need h prime of 1. This is the fun part. We need to take the product rule of this function right here. So what is h prime of x? H prime, I'll do arbitrary. h prime of x, and then we'll just plug in 1. H prime of x is going to be the derivative of the square root of x. Again, I'm hoping you guys have this function next to you. The derivative of the square root of x is 1 over 2 root x times g of x. Again, I'm using the product rule. Plus the square root of x times g prime of x. That's simply the product rule, and we know the derivative of the square root of something. And therefore, h prime of 1 is equal to 1 over 2 root 1 times g of 1 plus root 1 times g prime of 1. So we'll need to know what g prime of 1 is. But those of you paying attention, we already know what g prime of 1 is. G of 1 was 3. Then plus the square root of 1, which is just 1, times g prime of 1. But that is the slope of this red graph at 1. And we already have the slope. The slope is, we have rise of 6, run over 6, run of 6, which means 1. Oh my gosh, so many 1s. So this is the square root of 1 times 1. What is that? 3 halves plus 1, which is the same thing as 5 halves. Let's go. Finally, we're not done yet. Oh, geez. We have 5 halves, but this is the easy part. We just plug things into this formula right here. So f of 1 is 5. We have h prime of 1, 5 halves, minus h of 1, which is 3, times f prime of 1, which is negative 4, all divided by f of 1 squared. Simplifying, okay, so that's 25 plus 24, all divided by 50, and that's the same thing as 49 over 50. Almost pretty. Dang. I think it's still pretty. All right, this next guy, we got g of f prime of 3, and this is just an immediate application of the chain rule. So this is going to equal g prime of f of 3 times f prime of 3. So I need 3 pieces. I need f of 3. What is f of 3? Have we figured that out yet? No, we haven't. We need, I'll write this down. I'll go over here. We need f of 3, f prime of 3, and then we'll need g prime of f of 3. So let's figure out what f of 3 is. This is composition of functions. F of 3. So f is our blue function. So we have to recalibrate a slope here. We have to go to 3, which is around here, and ask what's the output of our graph for f of 3. In order to do that, we ask what the slope of this graph is. Well, we go from 1 to 5, which means that the output, goes from 1 to 5, which means that we rise 4. And then we go from 2 to 10, which means we run 8, giving me a slope of 1/2. But to figure out what f of 3 is, the output right here, what I have to do is, so each time I take a step along the x-axis, what this says is my output increases by 1/2. So my initial output at 2 is 1. When I take a step, go from 2 to 3, my output increases by 1/2. So that means I'm going to get to 3 halves. All right. In other words, f of 3 is 3 halves. This asks for the slope of f at 3, and we just figured that out. We have the slope. That's 1/2. Now what we need is g prime of f of 3, but that's the same thing as g prime of f of 3 is 3 halves. 3 halves. In other words, what we need is the slope of g when x is equal to 3 halves. I think that's something that we've already calculated. So here's my function g. G is this red function. What I need is the slope of this function when x is equal to 3 halves. 3 halves is in between 1 and 2. Oh yeah, we already know this slope. This slope is 1. We figured it out right here. The slope of this part right here is 1. For any of these x values, I know that g prime of 2 is equal to 1. I know that g prime of 2.5 is equal to 1. It's the slope of the function at that point. So this is equal to 1. And I have all of my pieces. G prime of f of 3 is equal to 1. F prime of 3 is equal to 1/2, giving me a final answer of 1/2. 1 times 1/2. All right, now we got r prime of 4. Ooh, so r is this guy right here. What I think I'm going to do for this guy is figure out r prime of x and then evaluate it at 4. So r prime of x is going to equal the derivative with respect to x of, was it f of x first? G of x first. G of x times e to the f of x. All right, let's figure this out. This is going to be a combination of the product rule and the chain rule. How this works is I first take the derivative of the first function, that's the derivative of g of x, and then I leave the second function unscathed. All right, so my second function is e to the f of x here. So I have e to the f of x unscathed. Then I add to it my first function, g of x, times the derivative of that other function. So the derivative of e to the f of x. This one's easy enough. That's just g prime of x. Times e to the f of x. Then I have plus g of x. But look at this, guys. We have the chain rule that we have to apply. I have that outside function of e to the power of something. What I know is the derivative of e to the something is equal to e to that thing. All right? So the outside function derivative is going to be e to the f of x. But then, of course, I have to multiply by the derivative of the inside function. And that's the derivative of f of x. Here we go. This is kind of pretty. We have g prime of x times e to the f of x plus g of x times f prime of x, that's this thing, times e to the f of x. So I just used the product rule and the chain rule and this new result that we found out in this video, that the derivative of e to the something is e to the something. I need to evaluate this at 4. All right, so I need 4 pieces. We need g of 4. We need g prime of 4. We need f of 4 and f prime of 4. Let's figure out what these are. G of 4. Where am I? Oh, here we go. All right, so g of 4. I'm along this line right here. I need to take 1, 2, 3, 4 steps. That's going to be before I reach 6 here. And I notice that each step I take, I add 1 to the output. My output began at 2. 1 step, 3. 2 steps, 4. 3 steps, 5. 4 steps, 6. Okay, so I have g of 4 is equal to 6. All right, and now I have g of 4 is equal to 6. G prime of 4, that's the derivative of g at 4. We already know what that is. That's 1. F of 4, okay, that's nice. F of 3 is equal to 3/2. If I take another step from 3, I'm going to add one more of my slopes, quote unquote. So I go from 3/2 to 3/2 plus 1/2, which is 4/2, which is 2. F of 4 is equal to 2. And f prime of 4 is going to be the slope of f at 4, and we just said that. That was 1/2. All right, I like this one a lot. So all we have to do is replace things accordingly. So this equals g prime of 4, that's 1. E to the f of 4, that's e squared, 1 times e squared, plus g of 4, that's 6, times f prime of 4, that's 1/2, times e to the f of 4, that's e squared. So what I have is e squared plus 3e squared. Final answer, adorable, 4e squared. All right, what else we got? Last one. H of h prime of 1. Okay, so this is a function composed with itself. H of h prime of x, all I have to do is follow the chain rule. It's just like the g of x in the chain rule is the f of x again, pretty much. In other words, this is going to be h prime of h of x times h prime of x. All right, so now I need two pieces. What the heck h prime of x is, and then what the heck h prime of h of x is. In particular, I want to evaluate these at 1. So what I really need is h of 1. We need h of 1 and h prime of 1. I don't remember if we've calculated these. H was that gross function. Yeah, so h of 1 is equal to 3. We do have this one already. H prime of 1, do we have that anywhere? Here we go. H prime of 1 is 5/2. Hey, we got lucky. H prime of 1 is equal to 5/2. Okay, but that what I need is h prime of 3. Okay. So in order to do this, I have this piece right here when I plug 1 in. What I need is h prime of 3, because what I have is, so h of h prime of 1 is going to equal to h prime of h of 1 times h prime of 1. I know a few of these. H prime of h of 1 is going to be h prime of 3. Again, that's because h of 1 is equal to 3. Times h prime of 1, which is equal to 5/2. So what I need is to figure out what h prime of 3 is. Hopefully somewhere I have a function for h prime of x. Notice over here, h prime of x is equal to this thing, which implies that h prime of 3 is equal to 1 over 2 root 3 times g of 3 plus root 3 times g prime of 3. Okay, hopefully I have what those are. Oh my gosh, so much function composition. G of 3, do I have that anywhere? I don't think I do. So what is my function g at 3? Oh, that g is so well behaved here. We go 2, take 1 step, increase by 1, that's 3. Take 2 steps, increase by 1, that's 4. Take 3 steps, increase by 1, that's 5. So g of 3 is 5. And we have plus root 3 times g prime of 3, that's 1. That's the really nice part of the graph. The derivative of g at 3, that's the slope of g at 3, and that's just equal to 1. I don't know, common denominators, I guess. Multiply top and bottom by 2 root 3, so that's going to be 5 plus 18, all divided by 2 root 3. No, that's wrong. Guys, hopefully you do better than me with your Alstro steps, because I just blundered. I deserve this. 5 over 2 root 3 plus 2 times root 3 times root 3 over 2 root 3. That's going to be 11 over 2 root 3. All right, we got h prime of 3. Coming back over here, h prime of 3 is 11 over 2 root 3 times 5 halves. Give me a final answer, 55 over 4 root 3. That was an epic chain rule question. That is something we got to be able to do.